Okay, Randa, this one's made just for you because you asked me to make a video of my favorite one. I forgot about it for such a long time that this isn't my favorite one, but I'm running out of options. So whatever you see, I hope you enjoy it. The lesson today is called Regression. It's way towards the end of the book, and we're talking about linear regressions, but also other regressions. I'm trying to extend the statistics behind this. Every once in a while, I may step over and show you what's going on in the book. I know that's kind of weird, but I just want you to see what we're talking about. And I may put some things on the board, and I may not. You may just get a voice recording of my lecture, but that's all I got. Okay. So we already talked about the lines of best fit. You see that diagram right there on page 688? They're showing several different possible lines that might go through there. And maybe the very best one isn't even included among those. But just looking at the data, you can get a pretty good idea yourself what the line ought to look like that goes through, that has as many points, many data points above as below. I try to get it as close as possible. And if you had to draw this line yourself, you could probably get pretty close to the real one if you just took some time to take your straight edge and count the number above and count the number below and try to get that. We're not doing that, as you know. We're using the tools that you've got, the calculator that you have. There are some words, though, that you're going to need to be able to talk about. Randa, this is the diagram we're looking at that talks right there, that talks about the residuals. That's what we're talking about right now, just so you know. Okay. If you take a look at the data points that they've got on page 689 at the top, you see how they've drawn those little dotted lines from the actual data point to the line of regression? And they've done, it's a vertical line going up from there. Those distances, those dotted distances, those are Y value differences between what the line predicts it ought to be and the actual data that we collected. Now, for notation purposes, the Y values that are actually on the line itself, those are, and it's just this book. I don't know. I haven't read a lot of other statistics book, but the one that's actually on the line is they put a little prime after it. If you're in calculus and have studied calculus, this does not mean derivative. It does not. It means the Y value pertaining to the line of best fit. And so it's of the form A plus BX. We talked about that yesterday where we put the slope last. All references to little a and little b in this discussion, B is the slope. It's backwards from what you learned in algebra. You got to get used to it. It's the way it is. When you do statistical tests in your calculator and they refer to little a and little b, you got to remember which one's which. Yes.
Why do we do it that way?
Well, I'm not absolutely certain, but I'm pretty sure that, as I said yesterday, engineers, statisticians, people like that, they want to know where you're starting. That's the first thing they want to see. Where are we beginning and how is it changing? For mathematicians and studiers of algebra and just regular high school mathematics that you've been in up to this point, we're much more interested in how steep the thing is and which way it's leaning. And then we'll maybe we transpose it. Translate it up and down. We do that. This is the least important, the least interesting to us. This, how the thing leans, how it changes. That's the rate of change right there, is more interesting and more important to what we study when we go through lines. For engineers, people that actually use this stuff on real life problems, they're more interested a lot of times in where you start. And then how does it change from there? Not always. Sometimes this is completely and totally irrational, irrational in the regular use of the word. Just a weird thing that can't be interpreted properly. But a lot of times we're more interested in where it starts. If that's the wrong argument and I am wrong about that, doesn't matter, get it down. A is the y-intercept. B is the slope when we talk about it in here. Okay. All right. So the values that are actually, that's what our line looks like. The values that are actually on the line that you're looking at in that diagram, we call those y prime values. And we call the other ones, the y values that actually belong to the point. So this belongs to the line. This belongs to the point, the Y value that belongs to the point that we collected for the data. And the difference between those two, that's a residual. Strange little word. But that's what those dotted lines are. The lengths of those dotted lines are the residuals. Now that you understand the concept or the idea of a residual, does it make good sense to you that the line will fit better if the residuals are shorter? Okay, there you go. That's when we discuss residuals. That's what the main thing is, to try to draw a line so that the sum, when we add up all those residual dotted line lengths, is as small as possible. If we can make that happen, then we've got the line of best fit. Does that make good sense? Pretty easy concept. It just takes a lot of explanation, all the notation stuff that we use. Okay, the next discussion they have right there is about the difference between a plus bx and ax plus b. Ooh, we're doing a plus bx. Next thing you see is a horrendous formula for finding a regression line, for calculating a and b with a bunch of sums. Just so that you know what I'm talking about, Randa, I'm looking at the top of that page right there. I think that's backwards to you, but you've seen this before. You know what I'm talking about. You all know how to find the formula for your regression line in your calculator. We trust it to do its job because nobody does this anymore. Happily, there are some people out there who understand this and know how to program it. Yay for those people, because they make our lives much simpler. Okay, so take a look at example 1. Let's see if we can do this. It says find the equation of regression for the line for the data in example 4, lesson 10 line. We're still going back. He's still got data listed somewhere else. We'll get done that. I think you've already done that. Found the line of regression. I'm not sure we need to do that. Notice what he does and thank your lucky stars that you don't have to do this. Look at these steps. All those numbers, all the accuracy for the decimal, so you don't have rounding errors. Yeah. Turn the page and get the picture.
Stunning.
Okay. Yeah, it is. Isn't it stunning? It's an amazing thing.
Oh, it's stunning.
It's what?
Stunning. Without, just take the G off.
Stunning.
Yeah.
Stunning. It's just stunning.
Yeah.
I got you now. All right. Okay, so take a look at example 2. He does the same thing again. Notice he does steps 1 through 3, completes all of that, and then he does all that stuff with all those sums. And you get that stunning picture on the next page. 693, the top of that. And even before those regression lines were drawn, just by looking at the data points, they aren't perfect, but boy, they sure look like they're linearly related. We expect R to be rather high. Okay. Now, I want to talk to you about the bottom of page 693. Because these concepts, not how to run your calculator, push buttons, but the concepts so that you know how to intelligently interpret what your machine's telling you. The regression line can be used to make predictions for the dependent variable. What's the dependent variable? What's the typical variable we use for the dependent?
Why?
Y, okay. The regression line can be used to make predictions for the dependent variable. You should use these guidelines when you are making them. Listen carefully. The points fit the linear regression line reasonably well. We've already talked about reasonably well. In statistics, a lot of times the details that are numerical are left out. Reasonably well. That's a subjective thing. But we know what it looks like, I hope. The value of R is significant. How do you decide if the value of R is significant? Yeah, check that table that we talked about yesterday and see if to what degree of confidence you're sure that R is big enough. Closer 1 or -1. And if we decide that it is within, past those confidence intervals, the R value is greater than those cutoff points on that table, then the conclusion is. Anyone?
There is no.
We just talked about this,
Objecting on.
which is what?
There is no correlation.
Yeah, they're not linear related. If we find that the R value is significant enough because it meets the criteria of the table that we talked about, the degrees of freedom, member of n-2. You get it beyond those cutoff values for 0.05 and 0.01 alpha levels, then you can conclude there's enough evidence that they are linear related. Okay? So that's not a big deal. And then 3 says the value of a specific X is not much beyond the observed values. That's talking about the residuals. At a particular X value, the Y value isn't very far from the line for any particular X. And then here's a weird one. Look at number 4. If R is not significant, then the best predicted value for a specific X value is the mean of the Y values in the original data. I'll be honest with you. I don't understand that at all. I really don't. I've got 2 question marks written right there, and I'm gonna have to go look that up. I tried to find it online. I don't understand what's going on there, because if you just took all the Y values in your data and averaged them, how is that a good predictor of any Y value on the line? But we gotta remember, R is not significant. It's like somebody shot the thing with a shotgun and we got points all over the place. And the line, we can find a line that goes through it, but R is not significant, which means we can't determine a linear relationship for sure. And so what we do is we just take all the Y values and average them. And that's our predicted X value. That makes no sense to me. They're not linear related. I'm not gonna try to predict anything. But that's what they said. I gotta look that up and figure that out, because I'm not absolutely certain what's going on. So cross your fingers and hope for a significant R value. And if not, I guess we'll average the Y's and say that's our prediction. I don't understand why we would do that. I gotta read some more on it.
Miss J, would it be just like centralizing it all to like one point?
Yeah, I guess.
I don't.
That could be, you could be right on that, and that seems as reasonable as anything else I've read. I gotta do some more study on that. If I find out, I'll let you know. All right. Okay. Take a look at example 3. This one says, use the equation of regression line in example 2 to predict the final grade for a student who misses 4 classes. Remember that example that we did? We decided there was a linear relationship between the number of classes you miss and your grade. More classes missed, the lower the grade, so it was a positive or negative relationship. Negative, because as one went up, the other went down, right? And I think we even decided the R value was significant for that example that we did yesterday. The question is now, what we're trying to do now is to carry a step further, is now that we've decided there is a linear relationship, we'll use the line to make a prediction. Do you all know how to find the prediction in your calculator? We taught you this in like algebra and probably math 2. Maybe even math 1 if you had a graphing calculator. Now we use the calc key for a value. You recall that?
No.
Okay. I'm gonna get my other calculator then, because I want to leave the data that I've got in this one to show you something later, and I don't want to erase it, so. So let's go ahead and grab that data that they asked us to do. Everybody do this problem again. So everybody find a line, check with your neighbor, make sure you got the same line so that everybody gets the same data. We're doing, y'all know where to find the example? It's example 2 in the previous section. I can find it.
It's on page 669.
Oh, page 661. Thank you for that. Y'all remember how to fit a window? That's much easier than I taught you the first time around.
Yeah.
All right. R value turned out to be. Everybody got that one?
-0.9.
Okay.
What do you do?
I'll wait till everybody catches up. No, go ahead and check with your neighbors and see if you got the same line and the same data and all that stuff. Check with each other and make sure. That's the hang up of using your calculator. One little mistake will cause you to miss all. Be careful.
I'm not even gonna lie, I don't even.
You do. I know you're just staring at the board, Randa, so I'm gonna turn this around. You can see the class working on this if you want for a minute. Everybody say, hi, Randa. Oh, that was enthusiastic.
Hi, Red.
There you go. There you go. Okay, so you guys checking with each other on this?
This is a terrible.
Okay. I got an R, somebody tell me what you got for an R value.
-0.9.
Negative 0.94.
Yeah.
Negative? Why negative?
Because it's a negative correlation.
So when you go to check the significance of this on the table, what are you gonna look for?
+0.9.
Because it's only the size of the number that's in the table. So just to practice that again, go back to the table on A20.
Got -0.24.
And what's the degree, or what's the degrees of freedom here?
It would be 5.
5. And 0.94 is well above even the 0.01 confidence interval. So we conclude that
There is a correlation.
they are linearly correlated. Okay, or linearly related. Correlated is okay. So we decided that it's a good one. Now go to your graph. If you did it right, the calculator should be graphing the line. You probably already have it in there. And what they want us to do in this section is to now use that line, now that we decided it's a good fit and it actually is reliable. We want to predict the grade for a student who misses 4 classes. This is the part that some of you said you don't know how to do. So once you get the line in your calculator, you go second and calc, which is above the trace key, and just hit value. What are you going to put in there for the X value? 4. And we predict that a person who misses 4 classes would get around an 88%. Now they may not be anywhere close to that. That's what we predict based on a line that we've decided is reliable. Got it? Okay. All right, moving on.
4.
Is everybody good with this one?
Yes.
Do y'all know how to find a value when you've got a regression line and decided it's a good one?
Yeah.
Moving on. Okay. Nonlinear relationships. It's okay. She can still watch you guys. You guys are more fun to watch than the stupid board.
Oh, I'm not in it, so I can do it.
Oh, we gotta fix that.
No.
There's Isaac Randa. He's the, I don't know what to call him. All right. Okay. Isaac keeps this class lively most of the time. He's the one that thought that it was what? Stunning. Stunning.
Yeah.
Okay. All right. Okay, what?
My line's not popping up when I'm.
What's wrong with you? People see my calculator's broken. I go, really? The calculator really? That's usually how it works.
I'll make this into a video for Brenda. Brenda, what is it?
That's yours.
Oh, what was his name? One of you, Brenda? I thought it was Brenda. Sorry.
Did you say hi?
I did say hi, Brenda.
Someone else's lunch, Dad.
So you're still having.
Oh, why?
What do you think about it?
Why?
You've never seen any sides on all it is. Hopefully she didn't get me taking my notes on camera.
I'm debating the video.
Isaac's like, what?
I would say it, right?
Isaac, good thing you're not in it. I was just. Oh my. I don't know. Let's go.
He just told me.
Yeah.
Yeah, me and Andrew are both gonna be on.
That coefficient of determination with the error. Yeah, that doesn't sound like he's involved. Now.
I forgot.
I don't know. I'm just gonna wipe it.
You really wanna use this now?
That was all captured. And this is considered.
That was a really weird line. I don't know what was causing it.
Okay, so we're not blaming Carter anymore for being ridiculous with his calculator.
Wait, actually,
So, that was kind of rude, but most of the time, it's the kid, not the calculator.
so the real question is what the Carter did to break this calculator.
Yeah, that's the thing, Carter. What'd you do? It's mess it up. Anyway, we reset it. Hopefully it'll work. Try it out, Carter. And if it doesn't, let me know again because once we do this calculator, because I cannot figure out why that had that line in that. It was weird. Okay, I may be able to find it later, but we're moving on. Okay. Example 4, you ready?
Yeah.
A model rocket is launched with an altimeter to record its height every second. The data shown in the table, identify an appropriate function model to fit the data. Then use technology or calculator to find the equation to model the graph in the scatter plot. So this time, put the data in just like you did before, list 1 and list 2. Just like before. And get that done. It's gonna take a minute, I know.
Are we gonna have to do something with the logarithmic function?
Possibly. I don't think so, probably not in this exercise. They're just showing you possibilities.
Okay, cause that would not be fun.
Oh, sure it would. Awesome.
Fix your attitude.
Oh, yeah, I'm excited.
Fix your attitude.
I'm just like.
It's gonna be what? Stomach.
Study.
Another word keeps coming to mind, but it's not right, and I can't say it out loud in class. Okay.
It's definitely quadratic.
See? Yeah, you look at your plot after you zoom stat it, and it's certainly not linear. This is what I'm getting. Which we expect from rockets. Okay? Looks like a. Okay. Tell me the difference between quadratic and a parabola. There is a difference.
Oh, heck. I got it. I was running too long.
Oh, come on.
Can quadratic be like x to the fourth and x to the second?
Well, those are polynomials.
Oh.
It's okay. Those are higher degree.
Parabola.
What's the difference between quadratic and a parabola?
Quadratic is the equation of the curve.
Thank you.
Okay, Cody.
The parabola is the graph of a quadratic equation. So this looks like it's quadratically related because the data looks like a parabola. Parabola is the picture, quadratic's the equation. Y'all know how to fit a quadratic?
Yes.
Okay, it's pretty easy. Go to the calc menu. Instead of down to 4 or 8, you go down to 5 because it says quadratic. Put the same information in from where it can find its x's and y's.
You want, that's the second count? No, it's statistics. Oh, and then it's just,
Oh, but then you need 5.
and then I want to store that.
Instead of.
We're gonna need to-
What do we get for an R value?
What is that square root of?
Don't
Oh,
do that. Don't do that. What do we get? This is a loaded question. What do we get for an R value? There isn't an R calculated for this. It's only calculated for lines. The R value in your screen. Anyway, you could find R by square rooting this.
Yeah.
Okay, but the R squared value is given to us, and we will talk a lot more about that tomorrow. But you only get an R squared value. Nevertheless, it's still pretty high. It's still going to be between 0 and 1. Why would it be between 0 and 1? Because you squared it. So if it were negative,
So
you
it's
squared it,
always
you'd end up with a
positive.
positive. So it's not between -1 and 1, the R squared value, it's between 0 and 1. And the closer to 1, the better the fit. So you can visually decide this too. If you look at the graph that the calculator came up with to go through those points, and by darn, it's pretty dang close. Which is the reason why the R squared value is awfully high.
Yeah.
So we are convinced that a quadratic relationship is pretty good for predicting this, okay? Besides that, it's an object, it's a projectile being thrown up. and comes back down. And that's very much influenced by gravity and a quadratic equation. Okay. All right, so that's another kind of fit. Turn the page, take a look at the example 5. It says, using several years of satellite imagery, scientists observed the rapid growth of a newly introduced floating plant species in a reservoir. What? You understand what's going on here?
Yeah, it's floating plant species.
Yes, like how are they able to detect what it is and look at it spread? Yeah, satellites zoom way tight into this particular lake that they're worried about, this stuff growing in. And it says, the images allow scientists to determine the area of the reservoir surface taken up by these plants over time. The data show this. It says, identify the appropriate function model to fit the data. We're not actually gonna do this one because it takes too long, but look at the points plotted. Look at the points plotted and tell me what you believe that looks like, based on your experience and all the math you've had up to this point.
Looks like an exponential.
It looks exponential, which is kind of what you'd expect.
Yeah.
Until it's been growing long enough and it has completely inundated the lake, and now some of the species are starting to die because it's having to start to compete, and then it turns into a
Logarithmic.
logistic.
That's right.
The kind that it grows exponentially first and then flattens out to a carrying capacity, remember? We are looking at the data that we've collected so far, the way it looks on that graph, we're looking at only the exponential growth part. It's still got lots of room to spread, is what we're saying, and it's not having to compete for food every day. Okay, so that looks exponential, and if you fit an exponential curve to it, turn the page, voila, looks beautiful.
Quite stunning.
It is quite stunning. Okay? So visually, we're pretty darn sure that's gonna be it, and we expect the R squared value to be quite large, near 1. Okay? All right,
I think that's Miss J's favorite word. Though.
one last thing, what's that?
I said, I think that's your favorite word. Though.
It is not, I haven't heard it before.
I don't even know where I heard that from.
You're just that kind of guy, coming up with new and cool things.
Oh, I definitely did come up with that.
Okay, let's move on to the next set of data and let's look at this real quick, because this is important. This part's gonna, a little different from what we've done so far. Okay, here's what it says. This is our scenario. A band keeps track of the number of attendees and the amount they earn from ticket and t-shirt sales at each show on their tour. Find and graph the equation of the regression line for the data in table 1011, which is here. Then identify any influential points, that is outliers. That's what we call influential points, outliers, and describe their effect on the regression line. Explain when an outlier should be excluded when summarizing the data trend with a regression equation. Again, we're not actually gonna do this because I'm quite confident you could. But look at the plot of this data. Just visually speaking, do you see any outliers there? If you think this is linear related,
Yes. Yeah.
which one?
Top.
Very last point, right? Just so you can see, it's the bottom of that page right there. We're looking for outliers. Can you understand that if we were gonna fit a line through that, at that point would have the effect of dragging the slope up?
Mhm.
Turn the page. Stunning, look at it. If we left that point in, take a look at the slope. If we take that point out, look at the next page in the same location. If we took that point out and regress the line, look at it. Now let's see what happened when we leave it in and when we leave it out, and how it might affect some decisions you might make. First of all, the R value in this, I'm just gonna tell you, is high enough to be significant. So we believe that the line's a good predictor.
With the outlier left in or with the ticket?
Well, that depends, and you gotta make the decision. The equation of the line that goes through those points, when they left the outlier in, hold it up, the equation of that line is 10.711x minus 69. Now this one's in the form mx plus b, like we're used to saying. That's the way they wrote it. Can anyone interpret that in the context of the problem?
With. As one more person attends, you make.
Okay, I gotta amend something. Hang on just a minute while you think about it, This is the one that you get when you leave the outlier, when you take out the outlier. So this is without the outlier, this is with the outlier, and it's y equals, and they have it up here, it is 18.286 x minus 2014.9. Pretty dang different lines, right? I'm gonna turn it back around here, so, well, one of them has a slope of 18, the other one has a slope of 10, approximately.
So for, with the outlier, after $2,014 with each additional person, you're making $18.
Yeah, forget the y-intercept doesn't make any sense here.
Okay.
The beginning amount is less than, this is one of those cases where the y-intercept is not that critical. It's those slopes. Anybody want to interpret those slopes in the context of the problem?
Yeah, per person that attempts.
Is X the number of attendees?
Yes.
Yeah.
Yeah.
Ah, okay. So that means that if we use the first line that has that outlier in it, we expect to make close to $18 a person at our next concert, if we use it as a predictable thing. Take the outlier out, you're only making a little more than 10. That's a huge difference. So that's why you want to figure with it in and without it and see how significant the differences are. And if they're pretty significant, we need to decide which one's really the best predictor. And usually it's the one without the outlier. The outlier pulls things off. The other thing that you can use this for is if you get a scatter plot of points in there and they pull it together and you get a line and it's pretty dang clear, it does not go through it. And the line that you found goes way off and it misses most of the points and it doesn't go through the way you expected. Then probably what's happened is you've got one data point wrong. You entered it wrong. It should have been 18.27 and you put 1,827, got a decimal point or something like that. That kind of a point way the heck out of your screen is going to pull your line way up and it's going to look really bad. That's when you know that you got to go in and check. If it doesn't fit through your data like you thought, you've probably got a bad data point, which serves as the same thing that this outlier did. Okay? So that'll help you make that decision too. Okay. I think I'm just about done. Let's go ahead and do the applying the concepts and see if we can answer those questions. It's on page 701. We're talking about the same thing we talked in the last applying the concepts. Braking time, braking distance according as a function of how fast you were going before you hit the brakes. Remember that?
Yeah.
Okay. Find the linear regression equation. We did that yesterday, so I'm assuming you can do that. What does the slope tell you about? Even if you don't know what it is, you can tell me conceptually. What does the slope of your regression line tell you about miles per hour braking distance?
It would be exponentially related.
Well, yeah, they would, because it's kind of curvilinear and exponent would fit it best. But if we look at a linear relationship like we got yesterday, which by the way, was close enough to the data points to still have a significant R value, very significant R value. Remember when we fit a line through it, even though it didn't look like it was linear?
Like 9.6.
So if you did fit a line through it, what does the slope of that line tell you about miles per hour braking distance? Yeah, every additional mile per hour, every time you go miles per hour up one, the slope tells you how many more feet you're gonna need to get stopped. Does that sound good?
Yeah.
Is it just common sense that you told me that, or do you know how to figure that out in case it isn't common sense? You don't know how the data are working out very well. Anybody remember the definition of slope from your algebra days?
Rise over
And what is rise associated with?
Y.
And what is run associated with?
X
And what is the y value in this scenario?
is the braking distance,
Braking distance and the x value?
is the miles per hour,
So if you go braking distance over miles per hour, what's braking distance measured in?
feet,
What's miles per hour measured in?
MPH
Yeah, it's miles
per hour.
per hour. Looks to me like, if you put one over the other, let's see, feet over miles per hour, if you compare that like that, which is the y value over the x value, right? You flip that over and do the arithmetic, hours over miles. Can you see that even though these are different units right here, I could put 5,280 feet down here and the feet would cancel? In other words, the distance units would cancel. What are you left with?
So,
Time?
it's time.
Does that make any sense?
Yeah.
I'm not sure it does to me. I gotta think about that one more. I kind of screwed up there. I'll make that make sense, I promise. I wasn't intending to go there and I thought the units would reconcile, they didn't. I gotta think. Okay, find the braking distance when the miles per hour is 45. Do you know how to do that? In your calculator, if you have the regression line, what do?
Great value count. 138.4 feet.
I think it was probably my belt, yeah, my mind's stuck. Anyway, you know how to find out the stopping distance for 45 miles an hour?
Yes.
How? In here.
Second calc or second trace. And the
Second trace and then choose
value.
value. Have y'all done that enough? You know where that is, okay? Find the braking distance when it's 100, same thing. Comment on predicting beyond the given data values. So if you're gonna use that line to predict braking distance, think it's gonna work?
No.
Not for very long, because you remember the data was kind of like this, although a line fit through it really well, but that line is gonna deviate from that curve more and more and more, so it loses its predictability pretty quick.
Wait, you guys are playing here for it?
Yes.
Oh,
What's the matter?
I did exponential regression.
Right. It does appear to fit exponential a lot better. The physics tells us it does too, or maybe quadratic, I don't know. But it is quadratic, velocity, squared, I think it's a squared relationship. But either one of those curves is gonna fit better than line. All I'm saying is, folks, is this, yesterday, the line fit through those, even though it didn't feel like a line ought to be the one we used, and when the line that we fit through, the data that we had fit really well. Remember that? What I'm saying is that your data looks like this. Started out low and it kind of went like that a little bit. We had a line that went through it like that. It fit really well. What I'm saying is that we all know this thing's kind of quadratic or maybe even exponential. We'd have to investigate. But that's going to continue up like that. Well, that's going to continue out like this. So the predictability, the predictableness of this line loses its value real fast. If we had an actual curve that fitted better, it would work out okay. So that's what they're asking you to do. Comment on the predicting beyond the given data values. You wouldn't, especially in this case, because you can tell the curve's gonna keep going up and the line's not gonna go as fast. Gap between them gets wider.
And the lesson
Or
are
use your head.
the
What's that?
lesson are we only doing linear?
I'm sorry.
Are we only doing linear regression?
Unless the problem says graph the data and fit the curve that you think fits the best. If that's the instructions. We will only talk about the R squared value for lines in this statistics class.
Okay.
But we also understand as we're going through that there are other curves that might fit better. Okay. So that table on A20 is really only good for comparing R values for lines, nothing else. Just R values for lines.
Okay.
Okay. All right, so this is, I have a few problems, not very many, a few problems for you to 7 of them. That's the end of the talk, Brenda. We're all gonna start working on it now. Sorry, this wasn't my very, very best performance, but there you go. I had to finish this up towards the very end.
Have you ended it
Talk
yet?
to you later.